Hi, my name is Kaylee and this is my submission for Lab 5. For this lab, I chose the Slinky video, and the purpose of the lab is to predict the motion of the falling Slinky. So the steps I followed was first to use Tracker to track the motion of the Slinky. I then wrote a glow script code to model the motion, and then finally, the main goal was to determine if the bottom of the Slinky stays stationary in the model like it does in the video. So some formulas and important ideas include Newton's second law, which is the velocity update and the position update formulas, and then also the F equals change in momentum over time. I had to write all the formulas out because I couldn't get the equation editor to work, but for drag force, F drag is equal to the negative proportionality constant times the absolute value of v squared in the direction of the velocity, and then the gravitational / Slinky force is going to be F grav is equal to negative mg j hat. And the Slinky force is going to be basically just F tension, which is going to be the same formula. Here is the tracked video. I'll just let it play. So as you can see, the center of mass is at the bottom of the Slinky, and for the purpose of this lab, the mass of the Slinky is 0.218 kilograms, and the height of the guy on the left was about 1.75 meters for calibration purposes. Let's see. Here's the code. This is the initial conditions. Line 36 is going to be the spring mass in kilograms. Line 39 is the initial position. Line 40 is the initial velocity, and line 57 is the drag proportionality constant, which I just thought were some important things to note. And then here is some more of the computational model. This is their first while loop. So line 66 is going to be when the bottom of the Slinky is constant, or the time when it's constant. 71 is the gravitational force. Line 72 is the Slinky force or tension force. 77 and 79 are the velocity and position update formulas. Here's some more of the code. This is the second while loop. 103 is the time until the Slinky reaches the ground. Line 108 is the gravitational force. Line 109 is the drag force, and then 114 and 116 are the velocity and position updates again. So here's the result of the computational model. As you can see, the orange is going to be the observed, and the blue is the predicted motion. So some errors that could have occurred: the motion isn't exact because there are other forces acting on it that the model is not going to be able to take into account. And then there's also the usual possibility of human error, like human inaccuracies while doing the tracker video and just picking each point. So the main question we're going to circle back to is, does the bottom of the Slinky stay stationary like in the video? The answer is yes, although there are some error and fluctuations. The bottom of the Slinky stays stationary in the model like it does in the video. And then finally, why does the bottom remain stationary? So the y directional forces cancel out because the downward gravitational force is equal to the force of the tension, which is going in the opposite direction. Since these are equal and opposite forces, they cancel, which causes the Slinky to remain stationary at the base. And that's it. Thank you. Have a great day.